Okay, we're going to talk about specific energy at this point, and we're going to cover the Froude number, specific energy, critical depth, and subcritical and supercritical flow, and talk about those flow regimes. A definition I want you to star or make sure you understand is the Froude number. This is this FR, and that's essentially the mean velocity of the channel divided by the square root of g times the hydraulic depth, where the hydraulic depth is this area divided by the top width. And so if you can follow this through, this inertial force, anytime you talk about inertia, you're talking about velocity. Anytime you're talking about a gravity force, obviously you got the gravity term in there. And so we're going to be talking about how these two things relate. This is going to be a very important concept to demarcate between subcritical and supercritical flow. And when we have subsonic versus supersonic flow, we use the Mach number, and the Froude number is analogous. It's a water kind of an analogy. You know, Mach number in terms of supersonic versus subsonic air travel in an airplane is analogous to what we think of in terms of subcritical versus supercritical flow, and the velocities play a big role in that, and we'll talk more about that in a second. Specific energy, if you look at the total energy at a particular location, that's the potential energy, the pressure potential energy, and the velocity head. And the specific energy is just part of that. It's just the pressure potential term and the velocity head, and I've defined it down here. If you essentially have using the continuity equation, we can express that in terms of Q by just making sure that the discharge is divided by the area to substitute that in for the velocity term. And so if I take a cross section of some given dimensions here, and you can see that on the left, and I have a particular flow rate Q, I can just plot a specific energy diagram where specific energy is along the x-axis and the depth is along the y-axis. And for various values of depth, I can calculate the specific energy through the specific energy equation. And so let's take a look at that real quick. If I've got a rectangular channel with a width of b at the bottom, I can, and for a flow rate of 100 cubic feet per second, I can assume a bunch of different values of depth and plug that into my specific energy equation, which if I start out here with the form in terms of in relation to velocity through the continuity, as I've mentioned, I can plug in q squared over a squared, which a is b times y, and I can come up with an equation for the specific energy of y plus 1.55 over y squared. So I just plug in various values of y and plot those along this curve, and I can see that this is the form of the curve. A couple things to point out, that for every point or every specific energy on this curve except for the minimum value here, there are two different values of depth that are potentially there for this specific energy. They're called alternate depths. Now, if you'll notice, we've mentioned that at the minimum location, this is where at C, that's where the minimum specific energy is. We can see that we have the alternate depths everywhere else. We can see that in this range, we've got what's called subcritical flow, and this is the supercritical flow range, where this is the demarcation between the two is at this minimum point with the minimum specific energy. So here are kind of a look at these things. As you know that Q is equal to AV, so that the higher the depth, the more the area, and if the discharge doesn't change, if this is constant, that as the area grows, that means the velocity has a decrease. So as the area up in this range is greater than the area down here, it makes sense that these velocities in this range are going to be much smaller than the velocities in these range here. And we talk about that here in this particular couple bullets. If I look at that minimum specific energy, I want to do a little bit here at development, because I'm going to remember that if I've got this, let's just really quickly here look at x and y. if I've got a curve that looks like this, the value of dy dx at the maximum and the minimum is equal to 0. So if I had, something that looked like this, like maybe a sine curve, we would have dy dx is 0 at these minimum and maximum points. That's something you should remember from calculus. And so as we move through here, I want to come up with a relationship of specific energy, the differential specific energy with respect to y, where I can look at that minimum value back when we were looking here. So I'm looking, okay, if I look and say, what is this dE dy when it's equal to 0, what can I say about that? So I've got to come up with an expression for dE dy for my specific energy. Now, as I take the differential of specific energy with respect to y, I come down and reduce it to something that looks like this, and I'll leave it to you to kind of review your calculus notes to make sure that I haven't made a math mistake or an error here in my differentiation. One thing I want to point out, if I've got dA dy, the differential of the area with respect to y, I can approximate this here being dA, this little square, okay, this right in through here, that's approximately equal to dy times the top width. Now we note that as you get farther into the channel here, that's going to be more and more of an error in that assumption. But we can rearrange that and say that dA is equal to t times dy, right? And so if I rearrange that, I can say that the top width is equal to dA dy, and I basically substitute the t in for that dA dy, and I come up with this expression for the differential of the specific energy with respect to y. Now, as I look at this, I can go back out to a term for the velocity here, just plugging back in if I get rid of the q squared over a squared and I just call that v squared, I notice that I define that the Froude number is equal to v over the square root of g times the hydraulic depth. If I square that, that's v squared over gd. If you'll notice here, this is none other than d. I can say that the differential of specific energy with respect to y is this 1 minus the Froude number squared, which is going to come in handy as we examine that minimum specific energy location on our diagram. So repeating that equation here, and I look at this location where I've got the minimum specific energy, and that's equal to dE dy is equal to 0. So if I set this equal to 0, I've got 0 equals 1 minus the Froude number squared. And we'll notice that then the Froude number is equal to 1 at this location of the minimum specific energy. All right. We can further say that at that location, if I've got 0 for that dE dy, I will note that rearranging this term tells me that the velocity head is equal to 1/2 the critical depth. And so as I look here and I say, okay, well, here is my critical depth value, and this is equal to YC, because this is a 45-degree line, that this distance here has got to be equal to V squared over 2G, which is also equal to DC over 2, or the critical hydraulic depth divided by 2. All right, so again, noted that the Froude number is equal to 1 at the case of the minimum specific energy. So I've said that right here. And as I've mentioned, or maybe I did not mention, when we look at this value here, the square root of g times hydraulic depth, from physics, you remember that that's a velocity of a celerity wave. And so if I take a quiescent pool of water and drop a pebble in it, I get a celerity wave that moves out at the square root of g times the hydraulic depth, the square root of g times hydraulic depth. And so if I've got, you keep that in mind, if I've got a stream that's moving at some velocity here that's greater than that VC, if I have a pebble or you get some kind of disturbance, there's no way that I can propagate my disturbance upstream. So that means I only have that disturbance is going to propagate downstream as the velocity moves. It moves so fast that it can't move upstream. And so that's the supercritical situation. And if we have a supercritical or supercritical situation, we can't feel the impact of anything downstream on the upstream of us. And so that's going to be important as we get into step backwater modeling, because we need to know if we have subcritical or supercritical flow, because if we have subcritical flow, we're going to model upstream because that's where the impacts are going to be. If we have supercritical flow, we only model in the downstream direction. All right. If we look at critical depth, that's going to be something that's going to be very important to compute. Froude number is equal to 1 is equal to the velocity divided by the square root of g times hydraulic depth. And that's going to be the equation we're going to use to calculate something called the critical flow depth. And so if we look at a rectangular channel and we realize that we've got this situation here with the critical depth, we can say that the velocity critical is equal to the square root of g times the depth critical. And if I further work this out here, I've got 1 is equal to q divided by a square root of g times the critical hydraulic depth. And remember, for a rectangle, the critical depth is area, which is b times y over the top width, and that's equal to b. So for a rectangular channel, d is equal to, the hydraulic depth is equal to just simply the depth, y. I can look at this and say, okay, well, in this situation, I can, rearrange this and say that q is equal to a square root of g times the hydraulic depth. And for a rectangular channel, q is equal to b times y square root of g y. And if I look and say, all right, I can define a small unit value, what's called the unit width discharge. That's equal to the total discharge divided by the width, q over b. That's equal to by square root of gy and divided by b. And you get rid of the b's. And so you've got this situation where the q is equal to square root of g d critical cubed. And again, this dc is equal to yc in this rectangular channel. So if I give you a flow rate, q, I give you a width of the rectangular channel, you should be able to tell me for that particular flow rate, what is the critical depth, yc. That's something that you'll need to be solving for. If it's another shape of channel, that's a little more complicated. If it's trapezoidal, you can no longer assume that the d is equal to y. You can't assume that, and so you have to remain using the hydraulic depth. If it's a irregular channel, sort of this shape here, let me pull this back up. If you have a irregular channel, what you have to do is you have to actually plot the specific energy diagram and find the location of the minimum specific energy, and that's going to correspond to the critical depth at that particular channel. So that's something that you're going to, just like on Lecture 10, I've really worked for you to understand calculating what's called the normal depth. In this case, you got to be able to calculate the critical depth. And we're going to put these pieces together to be able to understand demarcations between subcritical and supercritical flow. So I'm giving you building blocks. One of those building blocks was normal depth or the uniform flow depth. That was Lecture 10. Lecture 12 is understanding how to calculate the critical depth. And that's another building block to being able to understand some of the things we're going to work on later. All right. The other thing to remember is, just as we've said that at the critical situation, the minimum specific energy, the V critical is equal to the hydraulic depth divided by 2. If we plug that in right here to this part of the equation, we get that E minimum is equal to dc plus dc over 2, and that's equal to 3/2 dc. This is another thing, really good thing to remember, because if you remember this, and when I give you a problem in this where you have to actually, at one location in your problem, you've got a critical flow situation. If you know that you can plug this in for the specific energy at that location, that'll give you a shortcut to working the problems that really help. All right. For non-prismatic channels, in most of our discussion up to this point, remember prismatic means that the cross-sectional area doesn't change. For most of the discussion we've had so far when we talked about specific energy, we've talked about prismatic channels. And when we consider non-prismatic channels, that's going to help us, just the concept of specific energy, even though it doesn't really help, you can't theoretically apply that, you will be able to use the specific energy concepts to figure out what happens in a non-uniform flow situation. So let's think about that a bit. So as we look, and we've got this flow channel which has a bed here, and if we assume uniform flow, we've got the velocity and the depths don't change, so you start getting rid of a few things. Excuse me. And so we can see that the only terms we have left are the bed elevations at the inflow and the outflow and the head loss term. And so this is what we get. And again, if we divide through by the distance L that we've got, we know that this is basically the bed slope, S sub O. This is essentially the friction slope, S sub F. And as I've hammered home to you on lecture 10, that for uniform flow, the friction slope is equal to the bed slope. So if you look at this, uniform flow is an equilibrium kind of situation. That if we look here in the at section 1 up here, if this is my specific energy and it's uniform flow, it's at equilibrium, that's also going to be the specific energy at section 2, and they won't change. And so we can have two different depths there, and whether a depth is at y2 or at y1 in this case is going to be based on whether the slope is steep or mild. If it's mild, it's going to be a much slower slope. You're going to be in this range, the subcritical range. If it's much steeper, obviously you can think the velocity is going to be higher. I'm going to be in this subcritical, or I'm sorry, the supercritical range. We can use the specific energy diagram to predict what's going to happen. So we've got equilibrium conditions, uniform flow, but all of a sudden we put a bump in there. So what happens when we've got this nice situation that we had equilibrium, but all of a sudden we disturb it by putting in a bump? Well, what's going to occur is that when I have that bump in the channel, I'm going to speed the velocity up as I move downstream. And you can think of that like a riffle in a river that you maybe floated in your canoe. As you get toward that riffle, the velocity speeds up. As that velocity speeds up, it's actually moving faster than the equilibrium condition. So it's going to consume specific energy, or energy, quicker than it would have under the equilibrium conditions. And so as you look, you've got this little bump here in the channel. As the water moves downstream, it's going to consume energy faster than it would. So we're going to, if we're in the subcritical range and I'm consuming energy, that means I'm no longer in the critical flow condition. I've got to move down this specific energy diagram. So I know if I'm in the subcritical flow range, that at my location downstream, I've got to be at a smaller value of the specific energy than I did upstream. And so if you look at the graphic here, you can see that it's going to actually draw the water down because it's speeding up. You can actually predict what's going to happen based on the specific energy diagram. As we look, you can see here, this is not a bump, but this is just a drop off of going from one location to another. You can think of this as like a waterfall somewhere. And we go, and as we move downstream, the depth gets lower because I'm speeding up and I'm consuming energy to the point that I get to the minimum value. And at this point, you hit the critical depth. And as I keep flowing, now I'm into basically the supercritical range, and then I go over my drop. Typically, we think of the critical depth happening right at the brink, but that's not always the case. And so we have to approximate for that. And we can look, and let me get to this point. Here's the slide I'm looking for. That at the brink, that the critical depth is basically about 1.4 divided. The brink depth is equal to the critical depth divided by 1.4. So it's a little bit lower at the actual brink than it is at the critical flow depth, which that's just kind of an ancillary thing. You don't really have to worry about for computing problems. I'm just kind of giving you a little background there. This hydraulic drop is a situation where it's not quite a waterfall, where you got a vertical wall here, but you've got a slope downstream that's greater than the critical slope. And so we can actually create a critical flow condition, and then we get into a supercritical flow range here and that point of inflection. A hydraulic jump is something you have. Let's assume that you had some sort of flow that came down through here. Let's just put it right here. Let's say that I've got a sluice gate, and so I've got water ponded up here, okay? And it only allows it to come under the sluice gate at a certain depth, and that's going to be so fast that we're going to call that's going to be in the supercritical flow range. But it's on a slope that's mild or very flat, and it can't maintain that kind of energy, and so it goes through a hydraulic jump very rapidly. And as we look, let's go back here real quick, and let me erase this. Actually, let me move to this one right here. Let's get the eraser out. Okay. And let's get the pen back. As we are going in that supercritical flow range, all of a sudden we get to a point of instability, and it's going to jump all the way back up to the subcritical. It goes through this critical depth very rapidly, doesn't quite make it back around. This is a very unstable area of the flow, and so when it goes through this hydraulic jump, getting back over here to my hydraulic jump, it goes through very quickly, and so somewhere in here is the critical depth, and it goes back into the other location very quickly. All right, that concludes this lecture, and I now I'd ask you to go and work the problem.